So starting off is Alberto Madonna from ETH Zurich and CSCS to talk about HPC container services.
Thanks, Brian. Good morning, everyone. So, yeah, I've been working at CSCS for several years on developing and bringing to production, supporting production container technologies for HPC for the benefit of our users and the activities of the center. And the most notable tool and the most notable development across all these years has been the Sarus container engine. Maybe some of you are aware of it already, or at least have heard it mentioned somewhere. This tool has been in production for several years, now. And today I'm going to recap a little bit what has been the experience of CSCS regarding container technologies and the application of HPC containers, and a little bit offer on a perspective towards the future. So exactly, this is more or less the four steps where I have structured this presentation. A little bit of a story recap with the HPC containers at CSCS, broader perspective, and where we want to go from here. So the work that I will be presenting in this talk the work that has been going on and is still going on is the merit and of several people at CSCS, and I want to credit all of them, the people working with me on making this possible, and I'm very grateful to share this journey with them. So, as I mentioned, CSCS has been involved in HPC containers for quite a while. It started all the way back in 2015, so basically 10 years ago, with an early evaluation of Docker. Then in 2016, we started working to bring Shifter into production. Shifter is the very first HPC container runtime developed by NERSC. We opened that to our users in 2017. Eventually, we rolled out our own customized variant of Shifter. And then in 2019, we developed our own fully in-house container engine, which was called Sarus, and Sarus 1.0 reached PITS-Dyned, our flagship system, in late 2019. 2020, we enabled the possibility of building container images on PITS-Dyned, and eventually we, as the Alps research infrastructure progressively came online, we also deployed Sarus on Alps. And in 2023, we brought the latest iteration of our container offering called, collectively called the container engine on Alps. So as I mentioned, the most notable contribution that CSCS has brought in this space is this software called Sarus, and I'm going to offer a brief recap of it. Sarus is a container engine which combines the portability of containers with native HPC performance. And it does so by supporting container specialization and HPC features through OCI hooks, these modular plug-in components that can customize containers. Sarus also adopts OCI standards. It's compliant with these OCI industry standards and technologies. It integrates RunC as the internal runtime in the same way that Docker does. It supports hooks like the NVIDIA Container Toolkit for GPU access, and also integrates image conversion tools from the upstream community. One might wonder why we felt the need to create another container engine on our own while there were already a few around. So there were a few technical motivations for embarking in the Sarus journey. And to summarize, we wanted to create a container engine for HPC, which provided an increased focus on user-friendly performance portability and on-the-fly customization of containers. We wanted to have a tool that demonstrated the feasibility of a modular architecture integrating upstream components into HPC. So for example, these would be smaller programs and smaller utilities created not for HPC, but coming from the larger cloud and enterprise ecosystem. We wanted to demonstrate that it was possible to have a modular architected tool featuring them as well. And we wanted to demonstrate the applicability of OCI standards in HPC. So this has been in operation on previous Lumpitz 9 and now in Alps in some form since 2019, so 6 years already, more or less. And even as we rolled out, as we operated this on our systems and we helped users integrate containers in their workflows, we still realized that the difficulties that even having an HPC-focused solution, the difficulties of adopting containers in HPC were not really going away, because retrieving and running container images is relatively easy with almost any modern container tool. It's just at most 2 commands. Just pull the image and you run the image. And we can get up and running even a very elaborate, very sophisticated software stack in 2 commands. Okay, that's easy. But there is still a substantial gap between what you get with a container image that you can download from Docker Hub, from NGC, from anywhere else in the cloud, and what you need in order to construct a functional, usable context in which you can productively run HPC applications. And so maybe you need to figure out that you need to make some bind mounts from your host system into the container. You need to expose parallel file systems. You need to expose specific directories. Maybe you need to set the very specific, very particular environment variables for integrating with the system or to enable your specific application. Maybe you want the entry point from the image, maybe you don't. And then you have to consider all the possible plugins and hooks and customizations to enable specialized hardware, GPUs, network cards, interfaces with the fabric and the interconnects, all those sorts. So this creates a significant cognitive burden on users, for example, but also on the support staff. Because we have to figure out how to get containers on top of the existing infrastructure and on top of the existing environment. So there is this kind of, we like to call this a little bit of friction, a little bit of attrition between getting a container image and actually doing something in an HPC sense with it. And this is only multiplied if the things are not clear with what we want to achieve, like we are still developing the container image, or maybe we are still developing our own workflow. Maybe we need to do some debugging, so this only grows. And we wanted to do something about it, reduce this attrition between containers and the overall and their employment in HPC. So we set ourselves a new goal to increase the integration between container tools and the broader HPC infrastructure, which eventually translated into what we call making containers first-class HPC elements, full integrated, full ingrained in the machinery of a larger HPC infrastructure. In order to reach this goal, we formalized a concept which we're trying to put at the heart of our newest solutions, which is this idea of an environment definition file. Essentially, this is a comprehensive blueprint that represents, in a declarative fashion, all the different properties of a containerized environment. So, and it summarizes all the modifications that I need to apply to a generic container image in order to create an execution context where I can productively run HPC jobs and HPC applications. you can argue that basically arguably all of these modifications can be specified through command line options, a command line prompt. But this generates very elaborate and very long command lines, and moving all these modifications into a file, it gives us an entity that is not just easier to read or to write because we can give it a nicer syntax, but it is persistent. It can be shared. It can be composed. It's also composable. It can be tracked in source code management. And not only that, those are just the secondary advantages, in my opinion, because the introduction of the concept of this file representing an environment allows us to do something like this, where instead of explicitly interacting with container tools and like pulling images, issuing the container run, and explicitly tweaking all the knobs and switches that we need to get the containers to do what we want, we get a single option where we pass the recipe of how we want our job to be set up, not really the job, but the environment where our job is supposed to be run. And then I just interact with the workload manager almost as if I'm interacting with a native system, as if the container is not there. And what you're seeing in this example, this is basically an Ubuntu-based container running on Alps and leveraging the Slingshot network. This container was not built on Alps. This container was not present on Alps before this command was issued. I really would have liked to make a little bit of a more interactive demonstration, but Alps nowadays is busy on more, is completely dedicated to more priority work, more relevant work. So I'm falling back on a screenshot. I hope you can trust me on this. So in order to bring this idea, this concept, and this this experience to our users, we created a tool set that we collectively referred to as the container engine, the CE. Not very creative or descriptive name. I agree with that. So this is basically a forward-looking solution implementing this concept of containers as first-class HPC elements. And it is intended to enable containerized user environments on the Alps infrastructure. It is based on significantly customized versions of NVIDIA Enroute and Pixies, which are open source tools originally developed by NVIDIA. And on top of those, we poured all the knowledge and insights that we gather over years of operating Sarus, of operating Sarus and other HPC container elements. We published a paper at the Cray User Group Conference last year discussing the principles, the architecture, all the different details of where this Pathfinder is currently at. So for all the details, I encourage you to actually. It is not yet publicly available. It should have been, but it seems that we'll have to wait a little bit more before it is publicly available. But just so you know, there is going to be an official reference for all the details in this implementation. So this is more or less where we've been from the beginning. We started with Shifter, we deployed Sarus, and now we're transitioning to this new concept of containers as first-class elements with the CE. So let's stop a little bit there, and let's take a step back and have a broader look of what is happening outside, not just outside CSCS, but even in a larger sense, a little bit outside of HPC. And what is happening is, and what we see, the first thing we notice is that the cloud native ecosystem is continuing to grow, is continuing to evolve at a rather impressive pace. So what we are seeing here, this is a screenshot of the landscape of all the projects tracked by and part of the Cloud Native Computing Foundation. The Cloud Native Computing Foundation is a subsidiary of the Linux Foundation. And here we are seeing, like, these are more than 200 projects, which in 2024 collectively saw more than 15,000 commits per week. So an impressive and staggering amount of development going on in the larger cloud native space. Containers, of course, are a fundamental block of cloud native, so they move within the space, and they're very much also moved within this space. And the fact is that this cloud native ecosystem is not just increasing in size and sophistication in and of its own, but it's also evolving to accommodate and to enable AI. So AI is rising as a dominant cloud workload, and the CNCF has a dedicated work group in identifying problems and solutions to the application of AI in cloud environments. So of course, many container projects many container tools and elements are involved in this. So if we can align and adapt to the solutions and the systems the tools that we deploy in HPC on our own systems, there are significant opportunities which can be leveraged and that we can benefit from all of this overall ecosystem development. But unfortunately, with the current offering that we have at CSCS, we are not in a good position to keep up. Sarus was created 6 years ago with the main goal of running traditional HPC applications, and is missing many of the interactivity and manageability features that you would expect to find in more general purpose container tools. The container engine itself, it's a pathfinder to demonstrate this innovative user experience, but is based on software by NVIDIA, software that is not an officially supported product. It doesn't envision significant feature development and is not OCI compliant. It doesn't support open standards. The additional requirements that we both ourselves put and that are requested from users is getting very demanding in terms of the time and the expertise for the developers that we have to assign to these efforts. And at some point, we will also like to consolidate work from these two different activities. So where do we go from here? We have 4 baseline ideas that drive our future directions. The first is that our containers first approach is the way forward. The container engine showed us the value of this approach because it's also being used day by day on the machine learning platform of Alps. It's used very extensively by the Swiss AI initiative. We need just a solid foundation to back it up. The second baseline idea is that we recognize that upstream tools have matured to a point where many past concerns about the HPC integration are no longer hold. We want to continue on the philosophy that was of Sarus from the very beginning, the philosophy of leveraging open ecosystems and community, and enrich it for HPC, filling in the missing gaps with HPC integration. But we don't want to apply it to a single engine or to a single runtime. We want to apply it to a higher level, to the overall service architecture. And we want to preserve the value that we created with Sarus and transition it forward. So we are evolving, Sarus is evolving into a collection of software to unlock the power of HPC for community tools based on open standards. What I mean with that is that instead of having a single engine, collectively we will now refer at Sarus as a collection of 5 different tools, at least in its initial incarnation. And I will go very briefly over these 5 components. First, we have the the Sarus hooks. These are the tried and tested OCI hooks that have been developed and deployed alongside the Sarus engine up until now, supporting real-world use cases on PITS-Dyn before and on Alps today, MPI, libfabric, SSH, and more use cases. Now they will be shipped and published as their own project, no longer tied to the Sarus engine itself, so they might be mixed and matched with any OCI-compliant runtime. And we will also expand the documentation to explain how these can be integrated with newer developments like the container device interface. We will be working on a Spank plugin for the Slurm Workload Manager to enable containers as transparent job environments, basically what I showed before. And this tool that we provisionally call Skybox will implement the EDF concept and the container as first-class elements, first-class HPC elements idea. And eventually, we envision this to replace Pixies on CSCS and provide more features. We also have a storage tool to handle HPC container images in HPC, so to enable community container tools to leverage SquashFS-based images, basically the standard for HPC technologies in HPC container technologies, and to enable these images to be stored on centralized parallel file systems. Here we also have a significant influence of all the experience that we gather in operating Sarus and en route in real-world production scenarios. We're also spinning off much of the common code that powered the Sarus engine itself and the hooks into its own C++ foundational library. So we're going to use this as a dependencies of the hooks themselves, but if we're also making it, we will also make this open if anyone sees usefulness in having a C++ library for implementing container tools. And finally, we also envision a utility to distribute Linux subordinate IDs from a centralized source, for example, an LDAP cluster, all throughout the nodes of a computing cluster. And this is a problem. This is a very apparent problem if you try to deploy rootless container tools like Podman, for example, or anyone needing to use rich sub-UID ranges on an HPC cluster. And this will be based on a different tool by my colleague Miguel. Miguel, is he in the room? He is over there. Which we have deployed in production since 2020. This is also being present on PITS-Dyn as well, and then on Alps. So yeah, zooming back a little bit on the overview as well. So you might say, okay, this is all and fine. This is all well and good. Now, we don't have a single engine anymore. We have these 5 components. What are we going to do with them? So, well, the key terms, the keywords in this statement is that we want these new tools these new components to unlock the power of HPC for community tools based in open standards. And practically, at CSCS, we will use the Sarus components to augment Podman for the next generation of the container engine. So Sarus will be combined with Podman, and together they will be the core of our new container offering, collectively referred to as the container engine. How is this going to look like? It's going to look like a little bit like this. So this is a fairly elaborate diagram. I'm not going to go in the details, but what I just want to highlight here is that there is a backbone. Let's say, there is a backbone, and there is a main line of pre-existing components and open source components that support the execution of containers, and the Sarus components will come in to fill in the gaps in order to create a cohesive and fully integrated solution that is completely, let's say, fully interfaced and completely integrated in the overall HPC system, in the overall working of an HPC platform. So in conclusion, Sarus is evolving from an engine into a collection of task-focused components. These components will be open sourced and are intended to work separately and or in conjunction with other tools. At CSCS, we are going to use them all together to enable profitable usage of Podman in HPC. And the container offering on the HPC flagship system at CSCS will maintain a consistent user experience based on our EDF concept. And that's everything from me. Thank you very much.
We have time for a question for Alberto. Any questions?
If I take in HPC,
Mic on?
Can you hear me?
Mm-hmm.
Hello. Okay. So in HPC we used to use singularity in running HPC workloads, especially when it comes to some synthetic benchmarks. Now, if I compare that to Sarus with all this development there, just to my understanding, I'm expecting that definitely I don't need any more singularity. I should be able to run all this kind of HPC workload in the same way we had there. So I'm just trying to go for like a certain comparison to be able to see if I can scale, I can run these typical HPC benchmarks that we rely on and other stuff.
Well, yes, that is the minimum acceptable goal, of course, of enabling the maximum performance that the system can have into containers. This is one of the core objectives of all the developments that we have of all the works that we have done over these years for containers in HPC. This has been a main objective of Shifter, of Sarus, and it will be one of the pillars going forward. So we're basically accepting no compromise on performance. So definitely scalability, access to specialized hardware, minimum overhead. They're essential traits of any solution that we will bake in. So
Be able to access trivial GPU resources from the container?
yeah, of course. Yeah.
Thank you.
Definitely.
Okay, Alberto Madonna, thank you.